Hi everyone, I'm happy to be here for Lecture 8, Moderated Multiple Regression. And today we'll be reviewing the hierarchical and standard multiple regression that we learned last time. And then we'll talk a little bit about reporting and assumptions. Then we'll head into the major application of hierarchical multiple regression, which is testing interactions in regression. And as another example of unexplained changes of jargon, the test of the interactions in ANOVA is usually called a test of moderation in regression. So those two terms mean the same thing in the context of statistical analyses. Let me just also remind people that are watching this in the intended week that coming up soon is our regression quiz on May 4th to 6th. And that covers standard multiple regression, hierarchical and moderated multiple regression, but it won't cover mediation and indirect effects that we're going to explore in the week 9 lecture, which is delivered in week 10 because of Anzac Day. The second assignment is also released in week 9 and will be due at the end of May, or May 24th rather, at 4 p.m. And of course it has a multiple regression focus, and you won't be surprised to learn that the toots are essential in walking you through the skills and the write-up that you need to do well in the assignment. As soon as possible on Blackboard, we'll be providing feedback on assignment 1 and, of course, tips on assignment 2. And the tutorials the week of May 17th provide consultation for the assignment. Okay, so let's head into a review of week 7 and standard and hierarchical multiple regression. The main thing with standard multiple regression is that all the IVs are entered simultaneously in one block. And in a standard regression, you have two classes of results, the overall model fit, but also each predictor is evaluated in terms of its unique contribution after all the other IVs are controlled. And hierarchical multiple regression is a bit different. It has blocks of predictors. It could be one at a time, but it's often multiple predictors in one block, then another set in a second block, and so on. And these are entered in a sequential order based on theory, where each predictor is evaluated in terms of its unique contribution, what it adds to prediction at its point of entry, independent of all the other predictors in the model at that time, and sometimes shared variance, which is shared with variables in later blocks, is assigned to those earlier variables based on theoretical reasons. So last time we had an example of anxiety and motivation. The idea there was the anxiety comes first, and if there's a shared variability with motivation, then anxiety kind of owns that shared variance. But there's lots of ways of conceptualizing of shared variance, and it's very common for different researchers to have a different decision about how they're going to enter the variables in a particular regression model. And that's why one of the many reasons why multiple regression can produce unstable results, because if you change the order of your prediction, then the results will change. And so it's really important that the order of your prediction be based on logic or theory, rather than having had a peek at the data and changing your results after that. Okay. So, standard multiple regression, what do we test for? First, that global question. Do the models as a whole, do all the IVs considered together jointly account for significant variance in the DV? And that's the F test for the model R squared. When it's significant, it means that the R squared is different from 0. In other words, the null hypothesis is that the predictors together account for no variance in the DV. And if you've got a model that isn't significantly different from 0, then you've done a poor job at selecting your IVs. Then we also have a second class of tests. So first we report our model R squared test with the F. Then we report for each beta a t-test of significance, and that reflects its unique predictive value, how much its unique variability accounts for variance in the DV. The hierarchical multiple regression, you do report the F test of the model R squared, but you report it multiple times. You report the R squared change and the F change for every step, followed by a final report of the final model R squared and the F test for that. So we're able to say, like, the first few variables in block 1 account for 10% of the variance, which is significant. The next few variables in block 2 account for another 15%, which was significant. And the model as a whole accounts for 25%, which was significant. So whatever your numbers are, you're able to check out how important each of the relevant blocks is, plus how well the final model does. So it's more sophisticated in that sense. And again, we report for each IV, does it uniquely account for variance in the DV? The standard form of hierarchical regression, the normal form, is that you report each IV in its entry block. So if I enter anxiety in block 1, I report it in block 1. And if I have later predictors in block 2, I report them in that. And so visually, when we look at our Venn diagram of 2 predictors and a criterion variable, as shown here, in the standard regression, the model R² includes the unique and the shared variance. Each beta, though, for each variable only deals with the unique variability. And that's in contrast to the hierarchical multiple regression, where we're going to look at the model R² in block 1 and the model R² in block 2. And the variable entered in block 1, predictor 1, is going to be given shared variability with a later predictor entered in another block. So in this case, when predictor 2 is entered in block 2, its coefficient is going to be the same as if it was an SMR. But the coefficient for predictor 1 is going to look very different. It's going to be bigger because it's got the shared variability that's assigned to it and given credit for it. Okay. When we overall contrast the structure of the standard multiple regression and the HMR, then we can see that both test the overall model automatically, and neither one automatically tests for interactions. So those are the points in common, right? However, standard multiple regression doesn't test for groups of variables, which are called blocks or steps, and tests the unique effect of each independent variable. The shared variability is only captured in the model R² and doesn't come through in any of the betas for any of the predictors. In contrast, in hierarchical multiple regression, the variability accounted for by the model is reported for each block and then for the final model. So it's R² change and F change for each block, then the final model R² and F. And it also will report the unique effect of each IV within its block, but the shared variability with later blocks can be credited. So variables entered in earlier blocks will have larger coefficients oftentimes. Okay, I hope that sort of rings a bell, because you've watched last week and now you're watching this one, and you've hopefully been to your toots, which are so important. And also hopefully ringing a bell is the discussion of the writing. So for a standard regression, you're going to have your table of mean, standard deviations, and intercorrelations. Then you're going to have a report of the model R² with an F-test. Then you're going to have each IV's beta with p-values and also t's in APA7. And then you're going to have your SR² to provide the unique variance, and you're going to calculate and report the shared variance as well. In the hierarchical multiple regression, you do the same, only with additions that you reported for each block. So each block's R² change with the F change, each IV's betas with p-values as they're entered, report the betas for the IVs entered in that block, with T as well in APA7, and then SR² for the effect size estimate, and then a calculation of the shared variance in the final block and the final model R² with the F-test. Okay, so now the assumptions of multiple regression, and thanks very much to the student that pointed out that I had a review question for lecture 7, which had the assumptions plonked in there instead of in this week, but it is in this week. Oh, sorry about that. Because of the holidays, we're slightly restructuring the course. So variable based assumptions of multiple regression, as covered in week 8, include that both the predictor and the criterion scores, that is the IVs and the DVs, are normally distributed with a linear relationship between the predictors and the criterion, that the predictors are not multicollinear or singular, in other words, they're not overlapping wildly. We haven't talked about singularity yet. Those of you who are science fiction fans know that singularity is when everything collapses in on itself. And so multicollinearity and low parsimony, like we talked about before, the extension of that is when everything's just measuring the exact same thing. It's called singularity. And so if you have singularity, then the regression model just won't run. And another assumption about the variables is that they're measured on a continuous scale, which is interval or racial. And in fact, in regression, you can do non-continuous measures, especially if you use dummy codes or effect codes. We're not covering this in 3010, but you'll come back to it potentially in your honors year. So, in addition to those assumptions about the variables in multiple regression, there are other assumptions that we make about the distribution of residuals. The residuals, of course, are the error scores, so the observed score minus y hat. So that's your error or residual. Now, there's an assumption that these are normally distributed around the regression line. In other words, you do not have way more error at one end of the scale than the other. There's also an assumption that the variance of the dV is constant across the different levels of y hat, called homogeneity of variance, which is also called homoscedasticity, which is a fun term to throw around at parties, right? So homoscedasticity means that the variance of the dV is the same across all the levels of the predicted scores. And that signifies that there's no huge pileup of scores or error at one end of y hat or another. There's another way of saying that is that there's no linear relationship between y hat and the errors, so they don't increase as y hat increases or decrease as y hat increases. And more broadly, you have this assumption of the independence of errors. So multiple regression, as we've talked about it so far, makes an assumption that each observation is independent. It comes from a different person. It's not repeated measures. And so there's some complexity around that if you ever try and do repeated measures regression, which we're not going to cover in 3010, but again, you may come to it in later years or your honors year. Okay, so just to revisit this point of singularity, how do we know if singularity is observed, aside from the collapse of civilization, as in scientific science fiction film, rather? The multicollinearity is high enough to really affect your model when the predictors are super highly correlated. So a rule of thumb, anything above 0.8 would be, deeply concerning. The high intercorrelations of the IVs, remember we talked about collinearities, signal potential instability of the model, and the kind of associated statistic of that is tolerance. So tolerance is 1 minus the collinearities, where we're talking about a variable called r squared x, which is that overlap between a particular predictor and all of the other predictors. So the more that IV overlaps with other predictors, then the more there is a problem of tolerance. And so what we want is for tolerance to be high. In other words, we want r squared x to be low, the correlation of our IV with other IVs to be low. When we have multicollinearity, then the regression coefficients will be super unstable, meaning that if you add and subtract even a small number of people, the coefficients can change really radically. And that can lead to both type 1 and type 2 error, and you won't really know which. So we avoid this by thinking about parsimony, as we were talking about last week. Whenever your IVs are really highly correlated with each other, we need to consider dropping the redundant or repetitive variables, or combining them by averaging or factor analysis. And you'll learn about factor analysis in 4th year, so for now you're just responsible for that conceptual point that high correlations among the IVs is problematic. Okay, so this is an opportunity for another mini break. If you need to get a coffee or stretch or just pause before we go on to moderation analysis. Okay, so first let's revisit the conceptual similarity between moderation and interactions in ANOVA. So remember how in the omnibus tests, you check if there's an interaction, and if there is an interaction, you follow it up with simple effects. This exact structure is followed in a moderated multiple regression, which means a multiple regression which includes a test of interactions. So moderated multiple regression means a multiple regression in which we're testing the presence of an interaction. So what will happen is we're going to test for an interaction, and then if it's significant, we're going to follow it up. Our tests in regression, our follow-up tests are called simple slope analyses because we're testing what the slopes are at the different levels of the other IV moderator. And that's like the simple effects in ANOVA. So a simple slope is a follow-up test for a significant interaction in regression, just like a simple effect is a follow-up test for a significant interaction in ANOVA. So the meaning of an interaction in multiple regression is that the relationship between a focal IV or predictor and the DV or criterion changes based on the level of a second predictor. The second predictor is called typically a moderator. Common in regression is to use the language of enhancing or attenuating the relationship between an IV and a DV, and this just means strengthening or weakening. So a moderator that enhances the relationship between a criterion and predictor is strengthening the relationship of the IV to the DV, and a moderator that attenuates the relationship between a criterion and a predictor is weakening the relationship. So consider, for example, the idea that stress is associated with ill health, but it's moderated by social support, and the relationship between stress and health is stronger when you have lower social support. So what we would say there is that the impact of social support is that it enhances the negative association between stress and ill health, or the association of stress with ill health. Similarly, if we imagine that dieting is going to lead to lower weight, but that's going to be moderated by exercise, we can say the relationship between dieting and weight loss is stronger when there's increasing exercise, and that would again be reflecting a moderator that's enhancing the association of the IV with the DV. And so when we test in moderated multiple regression an interaction, it's just like in ANOVA. All we want to know is the impact of the focal IV the same across all the levels of the moderator, or is it different? The terminology is different in ANOVA and regression. So we're now going to refer to, in regression, our IV as X and our moderator as Z. And this is a historical tradition. If we visualize this as a series of circles that reflect, that show our predictor variables, we've already talked about the standard regression model, where the predictor is associated with the DV in a linear way. And so in that standard regression, it removes the shared variance and it doesn't test for any interactions. Rather, it assumes that there's no interactions. So in moderated multiple regression, we show that we're doing a moderated multiple regression by putting the moderator and having an arrow that points to the relationship between our focal IV and the DV. So this graph that looks like a T here is showing our focal IV, our predictor, leads to our DV, the criterion, but our moderator, which is Z, has an effect on the relationship of X to Y. That is, our moderator strengthens, weakens, eliminates, or reverses the impact of our IV on the DV. Now, one way of understanding the moderator, if it eliminates the impact of the IV on the DV, is that it's setting boundary conditions. That's essentially a disordinal interaction, as we've seen in ANOVA. Another impact would be if it changes the effect size by strengthening or weakening the effect. So it's the same effect, significant in all conditions, at all levels of the moderator rather, but the effect becomes smaller or it becomes stronger when you increase in your levels of the moderator. So if I ask you about particular hypotheses, I'd hope that you would be able to potentially draw what the interaction would look like and be able to speak about whether the simple slopes are going to be both significant, or perhaps they're going to be one significant and the other one isn't. So in this case, we might say eating increases weight only when exercise level is low. Right, so let's imagine how you might draw that. We'll just take a few seconds. Maybe you try and jot it down now on a piece of paper, or just draw it with your finger on the table. So we're going to say eating, when exercise level is low, eating increases weight. And when exercise level is high, perhaps weight is a constant at a lower level. And so being able to go from the hypothesis to the graph and discuss the simple slopes of the focal IV at each level, low and high of the moderator, that's something that would be good for you to know how to do. Now, how do we know how many simple slopes to calculate? Well, it's a little bit easier than in ANOVA, because in regression, traditionally, we only do two simple slopes. The simple slope of the variable when the moderator is high, that is 1 standard deviation above the mean, and the simple slope for when the variable is low, 1 standard deviation below the mean. So we're going to come back to that later this lecture, and you're also going to cover it in your tubes. But by convention, we only do two simple slopes, even though your moderator might have a 1 to 7 scale, so you could in theory do 7 simple slopes, or even like a 0 to 100 scale, you could do 100 simple slopes. But no one wants to do that, so by convention, if a regression is interaction in regression is significant, you're going to do two simple slopes, one for low levels of the moderator, -1 standard deviation, and one for high levels of the moderator, that's +1 standard deviation. Now, also included in the moderated multiple regression is the test of the direct effect of the moderator. So just like in ANOVA, where if we have two variables, we're considering their main effects and their interaction, a moderated multiple regression will test the direct effect of each predictor on the DV, but it will also test the interaction, which is the impact of the moderator on the relationship between the focal IV or predictor X and the outcome or criterion variable Y. And just as in ANOVA, we do not know anything about the other tests when we find out information about one test. So if I find there's a significant association between our predictor variable and our DV, that doesn't mean anything about whether there's an interaction. And if we find out there's an interaction, it doesn't mean anything about whether there's a direct effect of the moderator or a direct effect of the predictor. So we need to look at all three of these betas to understand what's going on in our data. How the linear model changes for a standard regression versus the interactive or moderated multiple regression is simply we have added in that interaction term to the structural model. So do you remember in ANOVA, where the structural model for the two-way ANOVA was, alpha j plus beta k plus alpha beta j k plus error and the grand mean. So what that was reflecting was that the score on the DV was a product of the main effect of A, main effect of B, and the interaction. So to here, when we look at the linear model for a moderated multiple regression, you can see that y hat, our predicted score, is a function of the first IV, the second IV, and the interaction. And each of those terms has its own beta, indicating how strong the association is. In other words, how powerful is the first variable in predicting the DV. The higher the beta, the stronger the effect. How powerful is the second one? And then how powerful is the interaction? Now, when I say higher, I just want to pause here and I'll highlight that by that I just mean different from 0. So if I've got a coefficient of +5 and -8, the -8 is actually a stronger coefficient because it's more different from 0, +0.5. So if I've got a coefficient of +0.5 and -0.8, then -0.8 is a stronger coefficient. Similarly, if I've got a coefficient of +0.2 and -0.3, the minus would be a stronger coefficient there. So it's more different from 0 that the coefficient tells us is a stronger association of that IV or interaction with the DV. Okay, so when we look at graphically representing the interaction in multiple regression, again, some people find it slightly upsetting. But what we're looking at here is a graph from last week, the regression plane, where we have additive effects only. And so what we can see in this graph is that there are an association between x1 and the dv, a negative association, that is the same at all levels of x2. So it's that same parallel line across the whole regression plane. The association of x1 with the dv doesn't change. And if we look at the next graph, we're seeing that the regression plane is warped or changed. And what we can see here is that when we're at high levels of x2, so plus 10 on this graph, then the association of x1 with y is a positive, whereas when we're at low levels of x2, a negative number on this graph, then the association of x1 with y is actually a negative. So the association between x1, our focal IV, and y, our dv, changes and in fact reverses in direction, a disordinal interaction, based on the levels of x2. So this visual representation shows the interaction in regression as a static image. This next section is an animation that shows the interaction at the top there changing and warping the regression plane. So for some people, this is really confusing and you just want to avert your eyes. But what I hope that you'll see, let's say we just focus on the slope for x1, that as the interaction term goes to 0 as a coefficient, meaning that there's no interaction, then each IV's association with the dV is static across all the levels of the other moderator. So the regression plane is totally flat. As the interaction becomes more negative, it changes in form so that the positive association of x1 to the dV at low levels of the moderator becomes negative at high levels. And then as the interaction becomes more positive, the coefficient becomes more positive, then the regression plane warps in the other direction so that the interaction that indicates, a positive interaction coefficient indicates, that as the moderator increases, the association of the focal IV to the dV becomes more positive, so it increases in slope to become more steeply positive. So for some people, this is not a helpful animation, but I know for some of you it'll really lock it in. So again, I just encourage you, whatever works. If you like the numbers, go to the numbers. If you like the formulae, if you like the words, if you like the graph, focus in on what is helpful to you. And always remember that the lecture is in some ways the first pass. And of course, when you go through this again in your tute and in the assignment, you'll really be locking in and consolidating this knowledge. I always love it when you guys make memes. I've been getting some hilarious ones. We'll be putting them into a future lecture. But in the meantime, I draw your attention to this classic from a couple of years ago. Each IV in multiple regression potentially adds a dimension of consideration. And the interaction, of course, indicates that the dimensions can warp each other. And so we quickly lose our ability to visualize as mere humans the awesome complexity of the data, but we can take a little stab at it with our animation, and hopefully that's helpful. Okay, another way of thinking about interactions in regression is to go back to our examples in the ANOVA model and imagine what it would look like if our IVs were actually continuous. So you remember that there was an interaction between alcohol consumption and distraction on ratings of limerick creativity. And at the time we had a distraction and a control condition, then we had 0, 2, and 4 pints. But let's imagine that instead of just having distracted or not distracted, we actually had a whole different number of levels of distraction and a whole different number of drink sizes. So you could have no alcohol or 100 mils, 200, 300, and so on. And then you could also be distracted by noises that were, say, 0 decibels, so no distraction, 30, 60, 90. And so what we can see then is that what was formerly a categorical graph is now a more complex, potentially, regression graph. And if we were going to look at all the possible simple slopes that we're showing here, we'd be showing the simple slope, the association between alcohol and creativity for each level of the distraction condition. In other words, or the distraction scale, 0, 30, 60, and 90. And of course, we could go on and on. We could have as many gradations as we wanted to of sound. Similarly, we previously talked about the silly and serious examples with none, some, and heaps of lecture preparation. These are categorical representations of continuous dimensions, right? So we can have no prep, 2 hours, 4 hours, 6 hours, 8, 10. We can have a continuous measure of lecture preparation. And then we could have a scale which was ridiculous examples to completely serious examples on a scale from, -3, very silly, to +3, very serious. And again, we could have a simple slope showing the association between our focal IV, which is lecture prep, and our DV, which was the exam mark, at each level of the moderator. And you can see here that it starts off with the outrageously silly examples, that the more prepared you are, the better the students do. And as you get more serious, it's like preparation flattens out, doesn't matter as much, and so you can just deliver the lecture and have limited impact on the exams. Up the top there, you can see that the rating scale continuum sometimes is criticized by reviewers or angry statisticians because technically it's ordinal, not interval. So for those of you who dimly recall in high school or first year where we covered this, ordinal is a scale where it goes in gradations of intensity, but it doesn't necessarily mean that the scale is the same or constant in its interval between 0 and so here we've got between completely serious and slightly silly and moderately silly. So that is an ordinal scale there, and it may be that the difference between slightly and moderately silly is smaller than the difference between slightly silly and completely serious. So technically with an interval scale, which is one of the assumptions of regression, as we learned earlier today, you can divide them in half and you can add them up, and they have equal intervals between each rating point. But we ignore this in psychology just all the time. So there are some reasons for that. Simulation studies show that regression can be robust to violations of the assumptions, and you can do regression with ordinal scales. But this is something that some of you will encounter in your honors and have to put a paragraph in the discussion of your thesis, where you talk about how the rating scale technically is not continuous and interval. It's actually only a Likert scale. It's only ordinal. Anyways, let's move away from that measurement point and come back to the point about how a lot of the factors that we look at in ANOVA could be changed into continuous predictors in a regression. And you'd capture a wider range, you'd have more possibilities to look at your simple slopes. At the same time, as we've highlighted, not everyone wants to do 7 different regression slopes or 100 different regression slopes if your moderator's on a scale from 0 to 100. So we've evolved some conventions, and we're going to go through that now. So the research question in a moderated multiple regression is, does the interaction between our IV and our moderator contribute significantly to the prediction of our DV? And so what you do in the moderated multiple regression is you put the direct effects in block 1, as if we're doing a standard regression with those 2 IVs. Then we enter our interaction in the second block. And when the interaction R² change is significant, that indicates that the interaction is significant. Then, as a follow-up test, only if the interaction is significant, not if the interaction is not significant, then you do the simple slopes of your focal IV at different values of the moderator. So imagine that UQ is interested in admitting students that are going to do well, and therefore they wonder how important is ATAR, the school performance marker, which is known to be a positive predictor of university performance, that is GPA. Now, of course, you guys would have come through under OP, but I changed everything from OP to ATAR because ATAR is the 2021 and onward high school criteria. So, recent work has shown that students with lower ATARs often get high GPAs in university. How can we explain this? That's a real finding, by the way. This data is hypothetical. One option is that, one possible explanation is that motivation to do well at university may moderate or influence the relationship between ATAR and GPA. So your high school grade will influence your university grade differently based on your level of motivation, and that's what we're going to test in a moderated multiple regression. So our default IV, our focal IV, I should say, is ATAR, and higher ATAR is better performance in high school. Okay, so the first thing you would do is look at your tables of mean, standard deviations, and intercorrelations. Here we're looking at the intercorrelations, and in red are our validities. Now, what is a validity again? I'm hoping that it's coming to you as you scrabble back in your mind to last week's lecture. A validity is the correlation of the IVs with the DV. So in this case, our two IVs are both correlated with the DV GPA. And so we have high-ish validities. Now, some people might be saying 0.3, that's not that high. It is actually pretty high for a real DV in psychology. In contrast, when we look at the association of ATAR and motivation, it's not correlated with each other. That's low collinearity. Now, low collinearity is good because, as we've talked about, collinearity can be associated with instability of regression coefficients. We don't want to have collinearity in this in these approaches. Now, sometimes people get confused about whether you need to have a significant correlation between the two IVs, or the IV and the moderator, for an interaction, and the answer is no. So an interaction is not looking at the linear association between ATAR and motivation, or one IV and another IV. What it's looking at, an interaction tests whether the association between one IV and the DV changes based on high or low levels of the moderator. So the correlation between the two IVs doesn't tell you anything about whether there's an interaction or not. So we want it to be low, and we want it to be low because that's low collinearity, which means better parsimony. Okay, so let's imagine that we're just going to do a standard multiple regression first. We can see that together ATAR and motivation account for 21% of variance in GPA, and the individual contributions are significant when we look at the betas in the second table. So ATAR is associated with higher grades in uni, and motivation is associated with higher grades in uni. Now, when we go on and ask the research question, what effect does motivation have on the ATAR to GPA relationship, we have to go beyond the standard multiple regression, which doesn't tell us anything about that. So we can pause now for another mini break and appreciate the humor in this depiction of the stress of moderated multiple regression. So instead of a standard multiple regression, when we want to test an interaction, we have to do an elaborated form called a moderated multiple regression. And it has 4 steps. They involve centering X and Z, our moderator, and calculating the interaction term, testing the significance of the interaction. If the interaction is significant, testing for simple slopes, and then making a graph to show the interaction. Now, I'm going to tell you what centering is in a second. It's a statistical technique that reduces collinearity between the interaction term and the direct effects. But I also want to highlight there's another macro in SPSS called process that will actually run the moderated multiple regression with less drama. So what we teach you here is good because sometimes you're forced to use the manual sequence in your analyses in your honors and elsewhere. But there is actually a shortcut that many of you will be able to take when you do your own independent analyses, and that you'll learn in 4050. That is the 4th year stats course. So I want to acknowledge that joy ahead of you and highlight that this information here that you're learning to use for yourself and for the assignment is going to be relevant to you in your future years. Okay, so I'm going to take a break now, and after that I'm going to go through each of the steps in moderated multiple regression in SPSS.